Good morning. It's 10 a.m. Central Standard Time here at the Dallas Environmental Education Center. Welcome to the Foster Middle School Dragons. And we appreciate you joining us on this cool but beautiful winter morning. If you're watching and you have not signed up, we appreciate it if you would go to www.tiny.ce/EEC, register, sign up. This is just for our attendance records, but we appreciate it if you do that. This morning, we're going to talk about global weather patterns. During this virtual field trip, students will discover that climatic interactions exist among Earth, ocean, and weather systems. Students will recognize that the sun provides the energy that drives convection within the atmosphere and oceans, identify how global patterns of atmospheric movement influence local weather, and identify the role of oceans in the formation of weather systems. Ms. Nash will talk to you about convection currents. Ms. Ramirez will inform you about the wind. Mr. Monroe will show you about weather maps, and Ms. Fuller will talk to you about hurricanes. During this field trip, this virtual field trip, if you have any questions, you can't raise your hand because we can't see you, but go to www.tiny.cc/EEC space question space answer. Send in your questions and we'll do our very best to answer them. Now I'm going to stop sharing my screen. And Ms. Nash will talk to you about convection currents.
Hello, welcome to my classroom. And today we're talking about convection currents in the ocean. So convection just means the interchange of hot and cold. It can happen in the air, it can happen inside the earth, it can happen in the ocean. And we all know that light, hot air rises, hot air balloon, and we know that cold things fall. They're denser, so they fall. So if you jump in a swimming pool or a lake, it will be warm on top in the summer and cooler down below. And that difference is what we call convection, when it turns over. Now I have my little lava lamp here to demonstrate convection. It's not working very well. I thought it was put completely. I think it sat too long, but maybe it'll warm up enough to work for us. But we're going to be looking at some different kinds of phenomena in the ocean. It's really, really interesting. And it's an important thing to understand because it determines a lot of global weather events and ocean temperature. So we need to think first about our Earth, which is a lot of ocean, planet ocean, really. Just like that Pacific Ocean, that's half the globe. That's amazing. And over here we have the Atlantic. So the equator, it's the hot where the heat comes from. The sun emitting lots of heat, but it's concentrated on the equator. And the poles, the North Pole and the South Pole, Antarctica, are colder. And that's not because the North Pole is actually warmer than the South Pole. It's currently almost frozen now. The slushy ocean used to be frozen ocean surrounded by land masses. It makes it warmer than Antarctica, which is a rocky continent surrounded by water, extremely cold. And so this is a lot colder than it, and that's important for our world system of convection current. So we're going to go look at some pictures to kind of try to understand this. It's pretty gigantic. Okay, so what we're talking about now are what we call thermohaline circulation. And it's driven by density gradients, meaning some water is denser than other. Temperature obviously affects density, but also in the ocean, importantly, salinity, meaning how much water, how much salt is in it. So salt, really super salty water is a lot denser. Hot water is less dense than cold water, and really salty or saline water is more dense than fresh. So we got the sun there providing heat, and then we've got the polar regions with their cold, cold, cold. Why isn't it working? Okay, so here's what happens. The surface water, okay, gets warmer and it carries the less dense water from the equator to the poles, and then as it gets colder, it sinks, and the deep currents carry it across the ocean floor around in that circulation. So as the water freezes in the Arctic and Antarctic, it becomes even saltier and therefore even more dense. The water coming from Antarctica is extremely dense, okay, much denser than the water coming from the Arctic. So we've got what we call the Antarctic bottom water, which is extremely cold and very dense. The North Atlantic deep water is also pretty cold. And then in the intermediate part, it's mixing. And then the Gulf, the top water, okay, from the equatorial zones is very warm. Okay. So it stratifies. So the hot water at the top, and then the cooler water down below, and then extremely cold and very salty water at the very bottom. This is the system. Okay, so we have the all around the Antarctica. There's a big current that goes all around Antarctica, and then it loops up and around a very complicated system. But basically, cold water is coming from the Arctic and Antarctic, getting warmed at the equator, and then getting cooled again and back. So the areas of convection are up here. Okay. Okay, in the Arctic. So as that warm water comes up, this is the Gulf Stream that keeps England and Western Europe from being as cold as the Yukon or Siberia. So they're actually quite warm because of that Gulf Stream. This is where it's getting mixed and cooled off and goes back down again. Also over here in Labrador in Canada. And then down here in Antarctica, again, areas of convection. So this is where the big convection is happening. Okay, now I'm going to stop sharing and we're going to try this for ourselves. Okay, so we're going to try a demonstration. So we know that lighter things float or are on top and heavier things sink. So we all know that. Let's try it with water. So I have a little tray here of room temperature water, and I've got a jar of icy water, okay, and it was in my fridge overnight. And I also, before I put it in the fridge, I dissolved a lot of salt in. So I'm gonna dye it a color, so maybe you can see it. Now, I tried this a couple times in my kitchen last night and I made a giant mess, but we'll try it again. So maybe it'll work better if I make a mess of it. So I'm going to carefully and slowly pour it into one side of the tray, my cold, very salty water. So what do you think it's going to be? Is it going to be more or less dense than my room temperature tap water? Make a prediction for me. What's going to happen? Let's see. The problem is, give it a minute. Let's see if it'll do it. Ah, it's doing it. Can you see how that cold, salty water even though I probably poured it too fast. You have to pour it really slowly. If you try this at home, be careful you don't make a big mess like I did. But try to pour it really slowly down the side, down the side of your container. So you can see it's really working. It's settling down. Can you see how that cold water settled to the bottom? And now we're going to try to have some convection. Now I have a little thing with hopefully still warm water. And smells like coffee. I'm going to put some red food coloring in this one. Okay. Now again, I'm going to try. I think I'll put it a little higher. All right. So we still got that gradient going on. Now I'm going to try to pour my hot water in over here. I'm going to try to pour it against the side. It's going to go down at first. So it's going down at first, and then you can see, I don't know if you can see it well enough. We've got a little bit of a convection current going on there, kind of mixing and trying to separate itself out. And, I guess it's mixed up too much with that super cold water and it got too heavy and sank on down. But it's a fun thing to try. You can try different amounts of salt in your water and try to make some stratification. So it's an interesting phenomena and I encourage you to find out more. So I'm going to turn it back over to Mr. Gorman for any questions.
Thank you, Ms. Nash, for that interesting experiment. And yes, we did have a question. What is an example of a convection current? And the Pacific plate in the Pacific Ocean is being moved, pushed around by a convection current. And now we're going to hear Ms. Ramirez tell us about the wind.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about winds. So I'm going to share my screen with you guys so we can start our presentation, and it might take just a second to get that screen share going, and then we'll start our presentation. So our first little thing that we're going to look at is an experiment that I did at home as well, and I want you guys to observe the video. So what you guys see here, I have a circular piece of paper. It's going to be rotating to represent the rotation of planet Earth. And then I have a ruler right here. I'm going to take a marker and I'm going to attempt to draw a straight line along the ruler. So what do you think's going to happen and what do you think that line is going to look like? Do you think it's going to look like a straight line or do you think it's going to look differently since the circle is moving? In this case, again, the circle represents, it says it's unable to play. So let me see if I show it from here, if it will play there, and it does it that way. So again, the rotating of the circle represents the rotation of planet Earth. We're going to say that the marker represents wind, and even though I am drawing a straight line across the marker or across the paper, using the ruler as a guide, hopefully you guys noticed that the line was not straight after all. It ended up being curved. So the reason for that is this example represents why winds are curving, and that is because of the rotation of planet Earth. So let me put it back in full screen and hopefully my other things will show up. So we're going to be talking about winds and wind patterns. And again, Earth's rotation plays a huge role in the path of our winds. So wind is simply air movement from an area of higher pressure to one of lower pressure. And air moves due to density differences from uneven heating of Earth's surface. So the apparent curving of the path of a moving object from an otherwise straight path due to the Earth's rotation is called what? And you saw an example of this effect in that previous experiment. And hopefully you guys said for number 2 that the apparent curving of the path of a moving object, or for example, the curving of winds, is due to the Coriolis effect. And hopefully, there it is, the Coriolis effect. And it'd be the same thing if you were to go on a merry-go-round and you were on one end of the merry-go-round, your friend was on the other end of the merry-go-round. If that merry-go-round is spinning or rotating and you try and throw a ball to your friend, that ball's path is going to be curved. No matter how hard you try and throw it straight, it's going to be curved because that merry-go-round is moving. Now, pressure belts and the Coriolis effect produce our global winds. And global winds are just winds that occur in belts that go all around our planet. And again, they are caused by the unequal heating of our atmosphere. So let's take a look at a diagram of some of our global winds and see if you can identify any of these global winds. Pay attention to the arrows. So what direction are these winds blowing from and what direction are they blowing to? Also pay attention to the latitudes that we see here as well. And then hopefully you guys know that here at the 0 degrees, that is our equator. So see if you can identify any of those global winds based upon this diagram. So let's start with number 1. So hopefully you guys said that number 1 represents the westerlies, and the westerlies are located on both hemispheres. So we have them in the north and the south. They are located, hopefully you were able to notice, between 30 degrees and 60 degrees latitudes on both hemispheres. And they curve to the east. So if you look at the arrows, the westerlies are blowing from the west and they are curving to the east. And they carry moist air over the continental US, producing our rain and snow. So let's take a look at number 2 in our diagrams. What do we call the winds that are between the equator and 30 degrees latitude? And again, we have these winds on both the north and the south hemisphere. So hopefully for number 2, you guys said the trade winds. And again, they occur between 30 degrees latitude and the equator. They curve to the west, and they're named because sailors actually relied on these winds to sail from Europe to the Americas. And then let's look at our last one, number 3 over here. These should be super easy. They're located at the poles. So hopefully you guys said that these are the polar easterlies. And they are between the poles and 60 degrees latitude, and they occur in both hemispheres, and they curve to the west. So again, you can tell from our diagram the direction that they're blowing from. They're blowing from the east and they're going toward the west. And these carry cold Arctic air over the US, producing snow and freezing weather. And then a couple of more, here's another couple of 2 more global winds. So let's take a look at number 1. So the winds that are occurring between the equator, and they are very calm winds. And the story behind the name of these winds, because these areas are super calm with very little wind, back then, you know, boats relied on wind power to move, so they had sails. Well, in these areas, there's not a lot of wind, so oftentimes those ships were actually stalled because there's no wind to move them. So oftentimes people, unfortunately, had to throw horses overboard to save on water and supplies. So the name for number 1 would be the horse latitudes, and they get that name because, again, the calming winds often caused sailors back then to, unfortunately, overthrow their horses. And then number 2, the super calm winds that occur along the equator. This one gets its name. It also means dull or sluggish. So these winds are called the doldrums, and they occur along the equator. And then we also have what are called local winds. So the previous winds we talked about were global winds. These are more local winds, and they blow over a limited area. They blow between small, low, and high pressure systems, and they're influenced by local geography. So for example, nearness to an ocean, a lake, or a mountain can affect these local winds. So we did a little experiment to demonstrate local winds with sea breezes and land breezes. So for example, and you can do this at home or at school, I just took 2 beakers. I filled one with water and I filled one with dirt, and I placed them in my classroom. Of course, the temperature for both was about the same, about 68 degrees Fahrenheit. I took those same 2 beakers and I placed them outside in the direct sunlight. And eventually their temperature was about the same. However, as soon as I took them outside, the temperature of the soil rose much faster than the temperature in the water. So this setup represents the daytime. Land will heat up faster than bodies of water. And because of this, if this were representing an ocean, this would produce a sea breeze. So cool air from the sea will blow onto the land, giving us that sea breeze. And that's what you see here. Again, that land warms up much faster during the day than the actual body of water does. And that's producing our cool sea breeze. And then to replicate the other kind of breeze, I placed both of these beakers in the shade, and the soil temperature dropped much faster than the water temperature. Now, it is important to note that eventually over time, the 2 temperatures in my experiment actually did level out to about the same. But when I first put them in the shade, there was a big noticeable difference in the soil one. So the soil temperature dropped much faster. This represents the nighttime because I put them in the shade. And this shows us that land cools down much faster than bodies of water. So during the night, there is a land breeze and cool air from land will blow into the sea. And then there's a diagram there. And then 2 more local winds that we're going to discuss really quickly. And that's valley breeze and mountain breeze. So during the day, sun warms the air along the mountain slopes faster than air in the valleys. This causes a valley breeze. And then at nightfall, the air along the mountain slopes cools and it moves down the valley, causing a mountain breeze. So those are just some examples of local winds. So my last challenge question for you guys, if you take a look at this little diagram from a news broadcast, how does dust from the Sahara end up in Texas? So think about that and what we learned about today. So I'm going to stop our screen share, and that's all I have for you guys today for global and local winds. We're going to pass it back to Dr. Gorman, and he's going to answer any questions.
Thank you, Ms. Ramirez. Yes, we had a question. What is our global wind? And it is called the prevailing westerlies. And now we're going to let Mr. Monroe tell us all we need to know about weather maps.
Okay, good morning, students. My name is Mr. Monroe, and my part of your virtual field trip today is to give you the ability to read a few weather maps. In fact, how many of you know what some of these symbols stand for? Of course, this is a basic surface map. Then, of course, scientists that use maps as a tool to forecast and predict the weather. There are a variety of maps. Now, this is probably the most simple. Of course, we know that snowflakes mean that it's snowing, but there are some basic symbols on here, such as this is a cold front, this is a warm front, but better yet, let me share my screen with you and we'll go over it in detail, okay? Okay, reading weather maps. All right. Now, a scientist that studies weather is called a meteorologist. Meteorologists make weather maps from information gathered using various instruments. Instruments used might include those studied early in your unit, such as Doppler radar, weather balloons, computers, and satellites. Of course, when you were in elementary, you studied about thermometers and anemometers and water, rain gauges, all those basic tools that meteorologists really use. Well, what's going on with this now? There are 6 basic types of weather maps. There's satellite weather maps. There's one that uses radar. There's one that will list the precipitation that's on the map, temperature, wind speed, and frontal. Here we're looking at a satellite weather map. And of course, this picture is taken from a satellite that's probably orbiting our Earth. And you can see that it's showing a variety of disturbances. Most likely, this is the front that we see here, but the satellite is not going to determine what kind of front that is. It's just showing that we have some disturbances that are going on that are above the surface. Here we have a radar map. Now, this radar map is going to provide images of what's happening with the radar. Here we see that these are rain clouds, or there's precipitation falling in this area. Back here, there is no precipitation. So radar is a very important map. In fact, I believe it was yesterday when we had the thunderstorm that came through. Well, I would have really liked to have gotten some pictures of that radar map when that storm came through. On my way to work, after the storm had come through, I noticed that we had some very tall images of what we call thunderstorm clouds, cumulonimbus clouds. Here we have a temperature map. Temperature maps usually have a lot of coloring on them, indicating that there is a change in temperature. If we look up here, the temperature in Vancouver, Canada is like 41 degrees. Winnipeg is 5 degrees. Dallas, Texas, 75 degrees. So that's an example of what we call a temperature map. Here we have a precipitation map that shows precipitation that is scattered all over the continental USA. And here it looks like we've got pretty heavy rains going on here. Maybe some heavy rain. Well, basically this is not heavy rains. This is snow and ice. Here we have heavy rains that are going on, and the lighter green usually indicates lighter precipitation falling. So that is an example of precipitation map. Here we have a map that shows the winds. Now these are sustained winds. Whenever we see a plus by the number, that indicates wind gusts. Well, it's pretty windy in some places. Here we see 16 miles per hour, 21 miles per hour. Let's see, wow, right there, there's something going on there. We've got winds that are sustained at 45 miles per hour. That's pretty strong. You know, with that thunderstorm that came in the other day, we had some pretty high winds, and I didn't record. I have a little weather station at my house, and I did not record the wind speed that we had there, but I'm sure it was well above 45 miles per hour. Front maps. Now, front maps are very, I really like to look for those, especially where we live in North Texas, because we get a lot of fronts. And you heard me say that on the surface map, the basic symbols are these. What we're looking at here, because they're triangles and the color is blue, that indicates a low air pressure mass that is sustaining probably a cold front. Whenever you have the half circles and a line, that indicates a warm front. Now, because the triangles are facing downward, that is the direction that that cold front is moving. It is moving to the southwest. This one is moving, the warm front is moving toward the north. Here we have what we call a stationary front. And actually the triangle and the bumps, they're facing opposite directions, indicating that that front is not moving. And of course, right here in the north part of Texas, we get a lot of those stationary fronts that will come down so far and then they just stop. And we also get, when the wind is blowing from the south, we get a lot of warm fronts. And then we have what we call print maps. And you can see on this print map, you see an H and you see an L. Well, those are actually indicators that that air mass that you're looking at, for example, That high, that H stands for a high, indicates that the air molecules are so tightly packed together, there is no room for any moisture to be in that air mass. And so what that means is there's not going to be very many clouds in the sky. In fact, there's a good way to remember what that H means. That means happy weather, okay? Now, on the other hand, whenever you have a low, that means that the air mass, the air molecules are kind of spread apart. It allows for a little bit of moisture to be in between those air molecules. And that means that weather probably is unstable. And you're going to have cloud cover involved with a low pressure air mass. And usually they say that a low will move into a high. Now, one thing to remember is that the continental USA is actually located in the Northern Hemisphere. And because it's in the Northern Hemisphere, most of our weather patterns will move from the west to the east, okay? Good thing to remember. And of course, if we look over here at the map legend, we can see that stands for cold front, warm front, stationary front, occluded front. Now, we don't get very many occluded fronts simply because that's a cold air mass, trapped in between a warm air mass, or they're trapped in between each other. And of course, there are a lot of other symbols. This symbol stands for a thunderstorm. This one stands for a light rain. And this one stands for a rain shower on a print map, okay? And usually wind direction is indicated with the arrow there. Well, that's about all I have for you. I've kind of run out of time. So I'm going to stop sharing my screen with you. And I'm going to give it back to Mr. Gorman. So if any of you have any questions, maybe he can answer those questions for you. I want you guys to have a good day today, the rest of the day now.
Thank you, Mr. Monroe. And yes, we did have a question, and it was, what is the most important instrument used in weather predicting? And that is the satellite. It's amazing if you watch the weather sometimes, what these satellites can do, especially when it comes to hurricanes and all. They fly right above it and just take pictures, just great pictures of it. So yes, the satellite is the most important instrument used in weather predicting. Now we're going to let Ms. Fuller tell us all about something that is very near and dear to me, and that is hurricanes.
Good morning, boys and girls. We're going to be talking about hurricanes today. So let me share my screen with you, and I'm going to show you some pictures and some short videos about hurricanes. So, and it's loading. Okay. It refused to connect. So I'm going to stop my share. We're going to try again, but we're going to do like Miss Ramirez did. We're just going to show it on the side, which won't be as impressive, and I think we're going to stop sharing. It looks like I might have lost my my presentation. Let's see if we can recover it. And apparently not. So
If you go back to start your screen share and then go to the bottom of your computer and open the Chrome icon again.
okay. It's still refusing to connect.
Oh no.
Yeah. I'm unable to load the file. I guess it was too large. Okay. Let's go back. See if I can recover it.
You were right. And then to drive. It might make you re-sign in.
Okay. Okay, I'm going to move this over. All right, so oceans and how they influence the formation of hurricanes. And what you see, Mr. Gorman Dr. Gorman made a reference to satellites. This is a hurricane. Over on the far right-hand side is Africa. And then you can see these little dots outlining North America over here. This is what a hurricane looks like from above. It's a cyclonic wind. And because of the Coriolis effect, which Ms. Ramirez talked to you about, above the equator, the cyclonic winds spin in a counterclockwise fashion. And below the equator, because of the Coriolis effect, they spin in a clockwise manner. And if you'll notice here in the center, we have what's called the eye of the hurricane, which is very still winds. Now, I don't know if this is going to play or not because of our technical issues here, but what you're seeing when I started, I'm going to go ahead and get it started. What you're seeing is the formation of Hurricane Matthew. You notice it's coming, and you can see the passage of night and day as we watch this formation. There it goes again. Watch the formation of Hurricane Matthew, but you see it's spinning in a counterclockwise manner, and it's heading from the east to the west. It's headed toward the Caribbean, and it only lasts a few seconds. So, but this gives you an idea of what it looks like as they form. Okay, so how do hurricanes form? Let's go ahead and get this started.
Hurricanes are wild, destructive, powerful, unfathomable. They are an example of how ruthless our beautiful watery rock can be. But how do they form? All hurricanes start out as a tropical storm. Then they feed off warm, humid air until they evolve into a giant, powerful storm. When warm air rises, it creates a negative pressure, causing cold air from the upper atmosphere to be sucked down into a low-pressure zone, like a vacuum, causing that air to warm. And the cycle continues like a big snowball effect until, eventually, a cyclone forms. Hurricanes favor the warm climates of the equator, where it's warmest on our planet and where the sun has the most exposure to the surface throughout the year. Humidity also plays a key role, which the outer equator is rich of, in areas such as the Gulf of Mexico and the Caribbean Sea. They contain warm waters, perfect to provide the flame needed to ignite a tropical storm. As water continues to evaporate and condense in the colder upper atmosphere, a tropical storm begins to form. If the conditions are right, it'll feed off the warm waters around the equator until a tropical storm forms into a larger storm and eventually a hurricane, which will then get carried by natural wind currents onto land, where they can cause their devastation. But why do hurricanes rotate? Well, it's very simple. Hurricanes are large storms that span hundreds of kilometers, so they are affected by Coriolis force, the Earth's rotation. This is why hurricanes are so turbulent and have very strong winds, and it's also why hurricanes north of the equator spin counterclockwise, while hurricanes south of the equator spin clockwise. How powerful do hurricanes get? They get very powerful. They are one of the, if not the most devastating form of natural disaster that routinely occurs on our planet. They can range from wind speeds of 119 kilometers an hour to 345 kilometers an hour, or from 74 to 215 miles per hour, mixed with heavy rains that can cause water surges up to 8 meters. If you ever find yourself in the path of a hurricane,
Okay, we're going to stop right there. That was Hurricane Harvey. That was from August of 2017. My part of my family lives down there, and that's what they experienced. Fortunately, their house did not flood, but they had 10 different families living in their house with them at some point or another, because so many of their families, their friends' families' houses flooded from Hurricane Harvey. Okay, now let's look at this. What's the role of the oceans in hurricane formation? Well, like he explained to you, you've got cold air overlying the warm, moist air of the ocean, and it starts that convection current that Ms. Nash talked about. So it's got this warm, rising air full of moisture coming on this colder air, and it just starts that circular motion and forms a tropical depression, which then if the water's warm enough when it gets out over the open ocean there on the Atlantic, it starts to feed it. The energy from the warm ocean water, warm, moist ocean air is the energy that feeds the hurricane. Now, I'm going to show you a little tiny, short little video. Now, watch Africa. This is where most of our hurricanes come from that we get here in the United States. So what's going to happen is warm air from the Sahara and moist air from down here are going to layer and then mix. So we got the cool, moist air from sub-Sahara Africa meeting warm, dry air from the Sahara. And they meet here at Cape Verde, right off the coast. And then it's got these strong winds. And so the combination of the warm air, the cool, moist air, and the African easterly jet, which is going to push it. And as it goes across the Atlantic, it's going to pick up all this energy from the 85, 86 degree ocean. And that's about how warm the ocean is in September. So there goes our warm, moist air. It's feeding the hurricane. And here comes the storms. And once it reaches 74 miles an hour, it's no longer considered a tropical storm, but it actually becomes a hurricane. And there's a Category 5 hurricane right there. Okay, I'm going to stop that. I'm going to show you how hurricanes are ranked. They're ranked 1 through 5 according to wind speed and damage done to property. The name of the wind scale is called the Saffir-Simpson Hurricane Scale. And we've had quite a few hurricanes of Category 4 and 5 hit Texas off the Gulf of Mexico. When you do your research on hurricanes, be sure and look up the 2005 hurricane year. That's the year that we got Hurricane Emily, Hurricane Katrina, Hurricane Rita, and Hurricane Wilma, all the same season, plus a whole bunch of smaller storms that did catastrophic damage. Wilma is considered the most intensive hurricane from the Atlantic basin because of the barometric pressure. So that's a really interesting year to study. And of course we had Harvey, and most of its damage was due to the fact that it parked over the Texas coast and didn't move, and it kept on drawing moisture in, raining, and flooded everybody. So if you have any questions about hurricanes, Mr. Gorman would be glad to answer them. Thank you.
Yes, Ms. Fuller, and thank you so much, and especially for that first picture, because it told exactly what I was thinking about the satellites. Now, the question is, are there any other names for hurricanes? Yes, some parts of the world call them cyclones. Some parts of the world call them typhoons. And my favorite, if you live in Australia, they're called a willy willy. Okay, again, thank you. During this virtual field trip, students discovered that climatic interactions exist among Earth, ocean, and weather systems. Students recognized that the sun provides the energy that drives convection within the atmosphere and oceans, identified how global patterns of atmospheric movement influence local weather, and identified the role of oceans in the formation of weather systems. Ms. Nash talked to you about convection currents. Ms. Ramirez covered winds, and Ms. Fuller covered hurricanes, and Mr. Monroe talked to you about weather maps. Okay, we'd like for you to tell us how we did. If you would, go to www.tiny.cc/EEC feedback and give us your input on the program, good or bad. We hope you enjoyed it. We hope you learned something from it. Thank you